formulas come from for arc length. And we're going to use them a couple of times today. And we kind of get into this mode of thinking that that lines and curves are so different that they can't be related. But we could actually find the length of a line segment with this as well, because technically a line is a curve, just with no bend to it, technically. And so we could actually use this as a substitute for the distance formula. So I've always wished that I could break into an Algebra 2 classroom or a geometry classroom and teach one of the students how to do this, and then have them do that on their quiz that involved the distance formula, just see what their teacher said. Because this is a legit distance formula, right? Integral from a to b of square root 1 plus f prime of x dx. But I have yet to find an opportunity to do that. Wouldn't that be fun, though? See if the teacher knows. Is this legit or not?
Math 9.
Totally legit. Yeah, and then just have them set it up in Math 9 it, right? Be like, okay, we're good. So we're going to we'll do one of these for you. I'll have you guys do the other one, and we'll tackle the last one. So example 1 says, find the arc length of y equals x squared on the interval 2 to 3 using x as the variable. We'll do that one, and then I'll have you guys use y as the variable. This really is pretty simple. Once you have this formula down, I showed you where it comes from, help you with remembering it. Bottom line is you would set this up like so. You would say arc length equals integral from 2 to 3. So the low x value is 2, the high x value is 3, and the integrand is just the square root of 1 plus the derivative of the function, in this case x squared. So the derivative would be 2x quantity squared dx. Now to evaluate this, Math 9 is going to be your friend. So take a few minutes or a minute here and evaluate this. Please don't forget the square root. That's happened before. And let's see what the length of a parabola is from 2 to 3. We're literally calculating how long the curve is. This is not an estimate. This is an exact number. Okay, give it a shot.
5.100.
Did you guys get the same thing? 5.100. Did you get it? I did get it. Okay. So, ladies and gentlemen, I want to go back up to the little statement above to make a point with this. It says, take care that the limits of integration, the function, and the differential all match. So as we transition into the other question involving this, we should get the same answer. We want to make sure that we can get there. And so the limits of integration and the function and the differential all need to be in terms of x or in terms of y, but it can't be a mix. So, Hayden, you with me? Okay, so I want to, again, point out that this interval from 2 to 3, that was in terms of x. That's how we used it in the first example. And of course, y equals x squared was y in terms of x. So when you use y as the variable, we should get the same answer. But the setup is going to look pretty different, right? Because everything is going to be in terms of y. So take a minute, convert everything over to y's, and see if you get the same answer. You should. I'll let you guys set that up. We'll check your setup, and obviously you can use your calculator as well to see if the answer ends up being the same. Use y's.
Use y. So the integral from 4 to 9.
Hey guys, could you quiet down, please? You said integral from 4 to 9?
Yep.
All right. Of what?
Of root 1 plus 1 half y to the negative 1 half squared.
Okay. So did you take that all the way through with Math 9?
Yep.
And did you get the 5.100?
Yep.
Come on. Okay, awesome. You guys have any questions about where any of Chandler's pieces came from? Within that? Hi.
I'm sorry, I'm from student council. I need to respect. Like actual houses or like cardboard? It's gonna be fun. Be there. Well, I meant like.
Okay, so we've got region R there. Point B is off to the right. That's the point of intersection. Region R is formed by the two functions x cosine x plus 4, and then that line. R is the region enclosed by the graphs there. And then the first part says just write an expression for the length of the boundary of region R. So in other words, just the perimeter of that region. And then use Math 9 to get an actual numerical approximation for that. So I'm going to let you guys run the whole way with this. You can use x or y, although I think one variable would be easier than the other. Take a few minutes, and let's do both. Let's set up the expression and use your calculator to approximate. Let's make sure that we're all clear on this. From a setup perspective, hey guys. Hey. I'm talking now. Let's go ahead and listen. Let's pay attention. Make sure we're all on the same page. We split it up into two different parts. We want to deal with the length of the curve first. At least I would, just get it over with. So the length of the curve would look something like this. Integral from 0. And remind me, what did you guys find for the x coordinate for the point of intersection? Okay, so x equals 2.094. Got to have that. Use your calculator, of course, to find that. So integral from 0 to 2.094, and you go square root of 1 plus, and then when you do f prime, you got to do the product rule. So it's x cosine of x, so it would be 1 d2 plus 2 d1, and then quantity squared dx. That right there would give you the length of the curvy part right there, but of course it wouldn't give you the length of the line. So with the length of the line, you can choose to use the kind of the old school distance formula, or you can choose to use the integral again. It'll work, like I mentioned. So we would just go, if I was going to do the integral, I'd just go plus, and then I would go integral from 0 to 2.094 square root of 1 plus, and then the derivative of the line will, of course, just be negative 0.5. So we plug that in right here, negative 0.5 quantity squared dx, and that would be your setup. At this point, carefully use Math 9. Did we come to a consensus on an answer? Was it 5 point something?
5.08. 5.508. That's what I have.
Okay, so length of the boundary 5.508. We do have consensus on that. Will, you get that too? Okay, good deal. All right. So guys, that's it for arc length. At that point, we found the length of the curve and the line. So we found the complete boundary, and we're done. Okay, let's go ahead and go backwards to where we finished last time with cross section. So go ahead and grab some Play-Doh. We'll make some stuff here. This will be challenging. See how you do with it. But grab some Play-Doh, and we'll do number 7. Okay, so for number 1, it asks us to rotate that region R around the line y equals 1. So that is a horizontal line as mentioned. So we would be doing something like that. We'd be taking that region, rotating it around that line. So see if you can imagine what that shape, the three-dimensional shape, would look like if you did that. What method do you guys see? It's got to be the washer method, agreed. If I was going to draw in a representative rectangle in the region R for question A, would the representative rectangle be a vertical or a horizontal one? Why vertical? Got to be perpendicular to the axis of rotation. So you're right. It'll look something like this. And it'll rotate around like so. And of course that sets the course for everything, right? How thick is that rectangle? Dx thick, that's right. Okay, so take a minute, see if you can write this down, see if you can set it up using x as your variable. We'll check our answers here in a second. If we're going to be rotating around the line y equals 1, you're going to get that shape that's created by rotation, right? Created by rotation. And so let's summarize it. Let's help Drew out because he's maybe a little confused, right? Yeah, am I reading you correctly? Okay, so if you're going to be finding volume by rotation, then what are the only two methods that I've essentially given to you guys?
Disk and washer.
Disk and washer. That make sense? Okay, if it really doesn't, we got to talk. That means the last 3 or 4 days have been a waste of time. Yeah, we'll do B in cross section. Okay, so of the two methods that were mentioned, are we going to use disk or washer?
Wouldn't we use disk since it
Oh, no, it's y equals 1, so you use washer.
It's, so you said it's y equals something.
Like it's over.
Oh, the displaced axis?
Yeah.
That's not always an indicator, although that's a pretty good indicator. Usually that's going to be the case, I would say. Just think about the shape, right? Like if you think about the shape that would be generated, the question I would ask is the shape going to be like totally solid, or is there going to be like any kind of a concavity or a gap to it?
I think it's completely solid since it's solid.
It is completely solid, I agree, but did anybody make this? Can I show him? Darn. Okay. Oh, Mackenzie, okay. So do you see how there's a big opening, like it's almost a bowl? So let me ask you this. At this point up here that you mentioned, and you mentioned it accurately, at this point right here, how thick would the figure be? Yeah, it'd be like 1 point thick, right? Remember me talking to Tess saying, notice how thin this is? It's like paper thin. That's what I was talking about. But notice like with Mackenzie's, do you see how it's like concave in the middle? That means we've got to use washers. If there's any kind of a concavity or especially a big old gap, like a hole in it, that's clearly washers. But even if it's just got a concavity, it's got to be washers. And the reasoning behind that is, think about this. Think about my representative rectangle right here. If I were to rotate that around, and if I were to draw like the kind of the image of it when it got rotated up above, isn't there going to be a gap right there? That means we've got to use washers. It's not going to be, not every single cross section will be solid. In fact, all of the cross sections will have little holes in them until you get to the very, very end. Does that seem reasonable? Okay. So if you're going to use washers, then what's the setup look like? I don't think so. So it's got to be in terms of x, to be honest with you. And the reason why it's got to be in terms of x is because the representative rectangle has to be perpendicular to the axis of rotation. And so that means we've got to use a vertical representative rectangle. And a vertical representative rectangle will have a thickness that's measured on the x-axis, meaning that all those are dx thick, which means everything has to be x. No, I disagree. 0 to 1/2. Okay, you said 1 plus? 1 minus, okay. 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 Tell me exactly what to write.
1 minus sine x.
Squared? Anything missing? Okay. Anything else missing? Am I multiplying the two integrals together? Subtract, yeah, okay. That would work, wouldn't it? Did you forget something? Am I not seeing something? Oh yeah, I am not seeing. You know, when you first didn't say it, I thought I made a little mental note, and I lost my mental note. Pi, right? Multiply the whole thing by pi. Sure, that would finally get us there. Okay, so any questions? Yes, ma'am.
You can do it in all one integral.
Yeah, I would prefer to do it all in one integral, to be honest. That way there's no need for the parentheses with the pi. You can do it in two separate integrals. That works. Just make sure the pi gets multiplied times both. Yeah. Any other follow-up questions? Let's maintain focus, folks. I would hate for you to, anybody, have a poor finish. So, is that good? All right, so we're going to shift gears a little bit. So I'm going to do some erasing from my picture. Because in question B, it does not ask us to rotate anything. In question B, it says, take that region R and turn it into the base of a solid. And for that solid, the cross sections are perpendicular to the y-axis, and they are rectangles of height 2. Yeah, so you can make this one with Play-Doh if you want, if you can handle it. I made it with Play-Doh. I tried anyways. There's my region. Can you see? Can you see my attempt at the graph there? Right, and then you got little rectangles popping off of the graph. So, I don't know, that's what I came up with. Feel free to use Play-Doh to make it if you want. You can also jump right into the integral. I'm going to see if my approximations are really rectangular. What's up? Let's see here. So you did. Okay, so you solve for x.
If it's perpendicular to y, does it have to be in terms of dy?
It's got to be y's, yeah. So is that a cube root? Yeah. Okay. So it'd be y over 8 cube root. Sure. And then you're going to have to do arcsine of y over pi. And so you'd go right side minus left side. And then times 2 for the height. That's pretty good. Yep.
So when you have to do an integral to get the area of the base? So
You never need the area of the base.
to find the volume you do.
No, you don't.
Isn't it cross-section problem?
It is, yeah. So you want the area of the cross section, not the area of the base.
So wouldn't it be this minus this with a height of 2?
Yeah, check it out. Jasper's not even here to appreciate my artistry.
Wait, would it be this way or this way? I can't figure it out.
What way or what way?
Like this?
Perpendicular to the y.
So how would I do that?
How would you do what?
How do I do my... So it's not like this?
You keep asking me half questions there. It's not like the way how I do this. Can you give me a more direct question?
Well, like I don't understand how the cross-section would be. But perpendicular to the y.
To draw these things in perspective, simply because it helps me see it. I hope that it helps you see it as well. So I would say y-axis kind of goes off into the distance. X-axis is right here. And then I've got my two graphs. And do something like this. And something like this. So there's my region. Does that make sense? So the cross sections are perpendicular to the y-axis, and so that means they would have to look something like this as a base, and then springing up from the base, it would look like that. So that means the thickness is measured on the y-axis. So they would all be dy thick cross sections. So like I said before, Hayden, you seem really concerned about the area of the base. But we really don't care about the area of the base. That A of x or A of y is the area of a cross section. So it's the area of the little rectangles. Give you guys just another moment here to get this set up, and then I'll help out. We'll have a chance to do maybe one more here. Volume equals, we're going to set up our integral. Our integral is we're going to accumulate from 0 to 1. We're going to be using y values there because we have dy thick representative cross sections. And then the only thing that really goes in the integrand is the area of each cross section. This will be a fairly good challenge. the area of each cross-section is going to be base length times height. And the height is going to consistently be 2, right? So I'm going to go ahead and just put 2 times. Now the base length is going to, like I said, represent a little more of a challenge. The base length is going to be essentially the red function minus the green function, but it's got to be in terms of y, doesn't it? So I'm going to take these two functions up here, y equals 8x cubed, and solve for x. So if I do that, I end up with what, x equals the cubed root of y over 8. That would be for the cubic, that would be the red function. And then the other one, y equals sine of pi x. If I solve for x on that one, it's going to be x equals arc sine, bless you, arc sine of y, all divided by pi. So we're always going to go high minus low, top minus bottom, or right minus left. In this case, it's going to be right minus left. So it's going to be cubed root of y over 8 minus arc sine of y over pi times dy. And at that point, my integrand is simply height times base, and the integral allows me to add up all of those little cross-sectional rectangles that will give me the final volume of the figure.
Question.
What do you think? Go ahead.
How can you add a bunch of areas and get a volume? Are we gonna have to?
Integral from 0 to 16, right? Cross-sections are squares. So it's going to be sides squared. It's going to be dx. And honestly, isn't the integrand really simple? What's the integrand? Yeah, x negative 1/4, and then of course squared. What would be the challenge? Because compared to what we just did, this one's pretty easy. What would be the challenge on this one? Because the left side makes this what? What kind of thing?
Oh, indefinite integral.
Not indefinite.
Irregular?
Not irregular.
Improper.
Improper. So here's what you'd have to do. Limit as x goes to 0 from the right. Not x, let's go b. Limit as b goes to 0 from the right. Integral from b to 16 of x to the negative 1/4 quantity squared dx. So my point is this, that it is very possible to mix improper integrals with something along these lines. So be aware that that could be a thing. So if you want to talk about anything else, please do let me know. Come see me sometime.